Hello, meteorology students. This is the third and final video for week one in weather and climate. This video will go over weather versus climate. We'll go over some weather maps with the size versus the lifespan of the weather phenomenon, and also weather versus climate. So let's get started. So first we're going to start looking at some weather maps. Okay, and before we get to the map, we need to have an important note here. Winds are actually referenced by the direction they're coming from, not going to. So if we have wind that's going from California to New Jersey, then that's going to be a westerly wind. Also, fronts are boundaries that separate air masses with different temperatures. So all it is, a front, is a boundary. That's all it is. On one side, an air mass is going to have one temperature, and on the other side, it'll have another. So just think about a front as a boundary. And the last thing is, on a weather map, an L is going to represent low pressure, while an H represents high pressure. That's pretty intuitive, but we need to make sure that you understand that. All right, so here's a surface weather map. Okay, this is in the northern hemisphere. We got to make sure that we state that because it's actually opposite in the southern hemisphere. But in the northern hemisphere, winds are going to blow clockwise and outward from the center of a high. So you can see here's a high, and you can see that the winds are going clockwise, but they're also kind of going out a little bit. Okay? Now, in the northern hemisphere, winds are going to also blow counterclockwise and inward from the center of lows. So here we have a low, and you're going to kind of see how the wind around it is going counterclockwise. They're also kind of pointing in a little bit. Okay, we'll go once we get into let's see, I think it's under pressure and different things that we go over in a few weeks. We'll actually go over the ramifications of what it means because the wind is kind of going outward or inward. But for right now, let's just make sure that we understand that around a high it's going to be clockwise, and around a low it'll be counterclockwise. Okay, now here's some fronts that we actually have. We'll go much more into fronts once we get into that section as well, but just so you guys can kind of get a little bit of an understanding of what they look like on a map, this is what a cold front will look like. It's always blue. The warm front is always red. The stationary front is always going to alternate between the blue and the red here. And the occluded front is going to be purple. Okay, so you can see right here we have an occluded front. Right here is where our cold front is. Over here is a stationary front. And then right here is going to be a warm front. Okay, you can also see on this weather map that we have some warm, humid air coming up here from the Gulf of Mexico. That happens quite often. See well, here I can see that it's coming that direction, not only because the arrow's here, but also because of our little station plot. Now, this is actually this right here is what's called a wind barb. And you can see the way that I describe it is going to be when you're throwing an arrow. So if you throw an arrow, the tip of the arrow is going to be the thing that's going through the air first. And the tail of the arrow is going to be the thing that's going to follow the tip. So if you look at this station right here, you can see like this being the tip of the arrow and this right here is being like the tail, then you can see that the wind is actually going to go down from the Gulf, and it'll be a southerly wind, right? Because we're referring from where it's coming from, not going to. So it'll be a southerly wind going, moving northward here, up into Louisiana, up into, what is this, Kentucky and Tennessee up here. So it's going to be going, from the Gulf northward, or being a southerly wind, so that air is going to be bringing warm and humid air from the Gulf up here to this area, and that is going to be what's going to be causing this air mass here, the separation between, this air right here, which would be colder, and this air right here would be warmer because this is the air coming up from the Gulf. So just to kind of start giving you guys some of these terms that we have and like how to analyze a weather map, we'll kind of go into it a little bit more when we get into fronts and different things like that. This is a great semester actually to take this class because in the spring we'll actually have tornado season and we'll have more severe weather. So it'll be kind of more. I think it's fun at least because I like to chase tornadoes. So it'd be more fun to kind of look at more exciting weather. Okay, like I said, we're going to go into the size and lifespan here. This is going to be they're definitely related in the manner that the larger the phenomenon, the longer the lifespan. So, and by, the flip of the coin, the smaller the phenomenon, the shorter the lifespan. So this would be a small turbulent eddy. What that actually is if you've ever seen, leaves blow in the wind, kind of like this or whatever. That's kind of what a small turbulent eddy would be. This is going to be like seconds to minutes. It's going to be on what's considered a micro scale, which is around 2 meters. Okay, so it's going to be a smaller type of thing, and it's not going to last as long. And then we're going to bump up to some like phenomenon called thunderstorms, tornadoes, waterspouts, dust devils. Tornadoes are going to be the column of air that's spinning below a thunderstorm. A waterspout will be a column of air that's spinning above, a body of water. Dust devil will be spinning over a desert or, some sort of dirt. And that's what's considered mesoscale. I actually take classes in meteorology called mesoscale so that we can learn about these things. But those types of things that are about 20 kilometers in size take minutes to hours. They don't take seconds and they don't take, days, but they're going to take around minutes to hours. Remember, a tornado is going to be small. Even if it's a huge wedge tornado, I mean, that's going to be, 2 miles at the most in diameter. So it's not going to be too terribly large. Now let's kind of get up here to like hurricanes and tropical storms. Hurricanes take up more like a whole state. When we've had these big hurricanes come through Florida and through Texas and areas like that, if you look at them on a weather map, they'll take up the whole state. That, because it's so large, that's considered synoptic scale. And that can take days, a week, maybe more than a week. Now, synoptic actually is another class that you take in meteorology. So that's a whole level of study to its own in meteorology. And then we could get up to these long waves. These long waves are going to be a wave that actually encompasses the whole globe. It's going to be like the jet stream. It goes around the whole globe. This global scale, is very, very large. And that's going to be, months it'll take to go around. It takes a lot longer. I mean, it can take shorter than a month, but think of it as being a lot longer because it's a lot bigger of a phenomenon. So these two things are very much related. The smaller it is, the shorter time period, and the larger it is, the longer it'll take. Now, here's some satellite photos. This is actually the new the new set. Let's see, this is GOES East. It was taken on August 26th of 2018. So this is the brand new satellite. I think I told you guys I watched one of these go up. These have great resolution. They're beautiful. You can see the picture that comes out of it. It's just gorgeous. Compared to this one's a lot older of a picture. I don't even know when this came from. It says like 2007, but it's I think older than that. You can see the difference in sizes of these things. Here's some thunderstorms, some individual thunderstorms right here versus here's a hurricane. Here's Florida to give you kind of a size comparison. You can see that a front would be more considered synoptic scale. It definitely encompasses quite a few states right here. So this kind of gives you an idea of how those sizes and lifespans are actually connected to each other. Here's some group questions. If you guys would like to pause the video and test your knowledge, I'd encourage you to do that. Okay, so here we kind of transition into, we've been going over this in this class is weather and climate, so we need to kind of go over what is meteorology, like what does it actually mean? Is this the study of meteors? No, it's not. I've had actually people ask me that before, but it's not. And you might wonder why we started using the term meteorology because it's not the study of meteors, but it actually is taken from a book that Aristotle wrote, and it was called Meteorologica. It was written in 340 BC, and he wrote about things like when it rains, it's cloudy out and very simplified ideas of meteorology that we all kind of intuitively might know. Some of it was right, some of it was wrong. It was about half and half. Obviously, this was written a long time ago, but that term meteorologic, that the whole idea of it just kind of like, I don't know, stuck. So at that time, meteor referred to any object that was in the sky. Okay, so like raindrops, snowflakes, anything was a meteor. And we've kind of kept that today because a raindrop in, meteorological terms is called a hydrometeor. So we kind of kept that. It's just not in common terminology. So when researchers began to specialize in, like extraterrestrial objects, which we call meteors, then the term meteorology was already being used in the context of weather because we were talking about raindrops and snowflakes. So that's when they started looking at other terms for that. It's about where the history of meteorology came from. Okay, so now atmospheric science. This is actually another, to me, it's an interesting term. My degree, my diploma actually says, degree of atmospheric science. So what that means is I've studied meteorology and climatology. So you can focus, like I focus more on meteorology, severe weather. I also focus on AI, those types of things. But there's other people that choose to focus on climatology, which is going to be more the statistical means and more of the long range stuff. So, but to understand atmospheric science is actually both. It's like an umbrella that encompasses both meteorology and climatology. So if you're interested in weather or climate, or you're a major, understand that atmospheric science is going to be kind of that term for both. Okay, so this is a really big deal right here, okay? If you walk away from this class in 50 years, the one thing I want you to remember is this. Weather and climate are not the same thing, okay? Weather is going to be the state of the atmosphere at a particular place and time. It changes a lot, okay, day to day, year to year. It's going to be what's happening here and now. It's going to be definite values associated to it. Tomorrow's temperature will be 80 degrees. That's weather. Now, climate is the accumulation of daily or seasonal weather events over a longer time period. So this represents a long-term average of weather, okay? But it also includes extremes, so like records that are broken. So I like to think of it as kind of being more statistical. Now, climate, generally speaking, will use 30 years as like the block of time that it'll use for that time average. And the reason why they chose 30 years is because apparently that's how long a climatologist's working span is. I don't know. But so 30 years is generally speaking what you're going to see as far as like the range. But if you're hearing something like the average temperature for San Jose is 60 degrees, that's going to be climate. The average rainfall for San Jose is 17 inches for the year. That's climate. Okay, so anything long term is climate, anything short term is weather. Now, you might be wondering to yourself, what about year, 1 year or another year? Oh, well, this year was really warm. That's still considered weather. Okay, so even year to year, you got to kind of step it up to at least 10 years to be climate. Okay, so over the last 10 years, it's been warmer than any other time period in history, which is true. That is climate. This year was really hot. That's weather. That is not climate. Okay, because it changes. You can have a really hot year, but our climate might be getting colder. So you got to know the difference between these two. Now, I have a favorite meteorologist. His name is Dr. Marshall Shepard, and he coined the phrase, weather is your mood and climate is your personality. I think that really kind of can help you understand the difference between these two terms. So a lot of people are confused by it. I see it all the time, honestly. People confuse those two terms. But please do not confuse those two terms. Okay, so here's some, we'll just go through some examples here. Okay, weather includes the variables actually that you'll use when you're describing weather are going to be temperature, relative humidity, wind direction, wind speed, cloud cover. I actually just Googled San Jose weather. I don't even know when I grabbed this screenshot. It's 75, so it must have been in the spring, in the fall session here. But this is all, every single thing here is going to be weather, okay? Tuesday at 3 p.m., partly cloudy, 75 degrees Fahrenheit. Precipitation is 0. Humidity is 52. Wind is 11 miles per hour. These are very much precise things that are happening on Tuesday at 3 p.m. I don't know which Tuesday, though. Okay, so, as we already mentioned, climate represents a broader average of weather for a region over a much longer time scale. You can speak on centuries or millennia when you're talking about climate as well. Now, like you might say, that we live in a Mediterranean climate. And that would be talking about, like, since the history of, the Bay, right? We do live in the Mediterranean climate, by the way. So the Mediterranean climate is like a longer time period, and that is definitely considered climate. So here's an idea. Sacramento, California is a city with this particular climate. I don't know what I was trying to say. Okay, so this I actually took, I don't even remember. Last year, I was driving to Vegas, and I drove through, and this is the place that had the hottest recorded temperature. Okay, 113 degrees it was that day. I think I snapped this. But it got up to, let's see, a record of 134 degrees Fahrenheit. It was measured on July 10th of 1913 in Death Valley. Now, is that weather or is that climate? That actually is climate, because remember, we're talking about extremes as well when we talk about climate. And since we're talking about the record temperature, then that word record should kind of key your brain to think climate. Here's some other stuff about the climate of Sacramento. Right here we're seeing what the lows are throughout, each month. Okay, up here on the x-axis, and on the y-axis we have the temperature. So you can see what the high is, on each of these months, and you can see what the lows are. It's the same type of graph. It kind of has the temperature, though, on the y along with the rainfall amount, and then the months on the x. So you can see that in May they get the most amount of rain. What is this? 4.75 inches. You can see here's the high, here's the graph for the high, and here's the graph for the low. The first time I taught this class, or maybe the second time, there was just almost a record. They almost made it. It was, let's see, they received 6.02 inches. The highest ever one-day rainfall at Eppley, 6.44. So they were super close that year. I would say August 22nd of 18. So they were really close to getting that record, but they just didn't quite make it. So I kind of threw this in here to kind of show you guys that this also would be an example of climate, because it's an extreme. It's pretty much the second, right below the first day for the most rainfall. By the way, here in San Jose, we receive 17 on average inches of rain in a year. So Omaha, that specific day, got almost half of what we receive in a whole year. Okay, so the last topic here is, what do meteorologists do? Most people, when I say that I have a degree in these things, they relate to the weather, on the news, and they say, oh, so I'm going to see you on news, which obviously I'm not on the news. So not all my meteorologists actually are on the news. Not all of us do this. This is a really old picture, like 1975 or something. Okay, so, but if you are on the news and you choose to do that, this is what your job would actually look like. A little bit different today, because this isn't 1975 anymore. Look at that TV. Anyway, what most meteorologists really do is going to be weather forecasting. They predict storms, tornadoes, hurricanes. They might advise industry on upcoming climate. I used to work at Omaha Steaks, and they had a weather person there that would help them understand when to put more dry ice into the coolers when it got really hot in different areas of the country. But then there's people like what I do and my coworkers do, and a lot of the people that I graduated with, they work in the government sector. They actually do more atmospheric research. So they're looking at things like climate change. They might be looking at ozone depletion, how much CO2 is in the air. They also might look at hurricane. I have a friend that works at the National Hurricane Center. They might look at tornadoes. Some of them might be looking at El Nino. So, they're going to be doing research in different areas of the atmospheric sciences. Um, Not sure why this picture is in, why these are in here, but I think just to really exemplify what the tools that people that are meteorologists use. We might be using things like radar, satellite. Progress a little bit since here, but this kind of gives you the idea of the type of tools that meteorologists actually will use. Here's a great picture, a satellite picture here of a hurricane. You can see the eye there. And, I was telling you about the global scale here. This is what I was talking about, like these big Rossby waves, the jet streams will actually come through their global scale. Here is, say, it looks like measuring ozone. So there's the ozone hole. I definitely have seen a few of these different ones because it shows, how it's changed through time. Here's another graph showing you what El Nino will look like. I don't know if you guys will be able to see this because my face will be over part of this. But, kind of interesting because if you look at the axes here, this is actually the equator. So this is going to be latitude and longitude on each one of these. And then here's some questions for you guys if you guys want to try and answer these and use that for your studying. So this is pretty much the end of this week's lectures. Trying to think if there's anything else I want to tell you guys. Don't forget to do your discussions. I did put up homework for you, and I will open up the first quiz. So I hope you guys have a great week, and I guess you guys will see from me next Monday. Bye.